Mathematics, how much gold can you hold in an elephant's ear? When it's noon on the moon, then what time is it here? If you could count for a year, would you get to infinity or somewhere in that vicinity? When you choose how much postage to use, when you know what's the chance it will snow, when you bet and you end up in debt. Oh, try as you may, you just can't get away from mathematics.
Good morning and welcome back to another edition of Grade 11 Physics Online Edition. And I'm glad to have you back. I hope you enjoyed your spring break and that all went well for you. You were able to relax and enjoy some family time, get outside, enjoy some of the nice weather before the snow came. So as you've probably already heard, last week they announced that schools would be, or in-class lessons would be suspended indefinitely, and so we don't know when we'll be back in our classroom. Hopefully it'll be sooner than later, but that's okay. We'll continue to do it this way, and as always, as we go through things, if you have questions, make sure you ask them, make sure you email me in your questions, and we'll be sure to respond to those in our daily videos. And so again, Connect is going to be your main resource, so make sure you're checking Connect daily. Hopefully it's working better now as they've had some chances now to upgrade some of their systems, and we'll go from there. All right, as we get started today, yesterday was Palm Sunday, and I was reminded that when Jesus entered Jerusalem, people were laying down palm branches and singing Hosanna, King of Kings, Lord of Lords. And those people had certain expectations of Jesus. They expected him to come in as a conqueror and become king of the time. And Jesus totally upended those expectations. He far exceeded those expectations. And so yesterday in church we were reminded that Jesus is the expectation exceeder. And so no matter what your expectations are of how school will look or how the school year will end or what this will all look like, what the world will look like when this is all over, just know that Jesus will exceed any and all of those expectations and that he is the King of Kings and Lord of Lords. So as we get started today now, I want to remind you that we've been doing an electric unit, an electric forces unit. And today we want to look at electric fields. And so last week when we were doing this, we were looking at electric forces. And so we realized that when we had two charged particles, we had opposites that would attract to one another. We had like particles that would repel one another, and they would do so with a certain amount of force. And so we came up with our formula. That was K, Q1, Q2 over R squared. Well, today we want to look at electric fields. And this is, again, a relation to magnetism. Now, magnetism you can see and experience because you've all had magnets at some point in your life. And you know that there's a magnetic field surrounding a magnet. Well, just like that, there's an electric field that surrounds a charged particle. And that electric field is present no matter what, no matter whether there's another particle in relation to it or not. All right, so surrounding it at all times. And just like magnets, there's a particular strength to it and a direction to it, right? If we bring two magnets together, or a magnet and a piece of metal together, we know that it will be attracted with a certain force. And the closer we bring those two together, the stronger the attraction is, or the stronger the repulsion is if you're bringing two magnets together. And so, same thing with electricity. When we have a charged particle, there's a field that surrounds it, and that field has a strength, and it's called the electric field intensity. And there's a direction to it as well, and a strength. And we want to look at that today. So on the board behind me here, I've drawn two charged particles. I've got a positively charged particle that we want to determine what the field strength of it is. And so to do that, we bring in a test charge. Now the test charge is always going to be positive. And again, it's a convention that we take to be doing all the time, the same way all the time, because that gives us a consistent result each time. All right, so the test charge will always be a positively charged particle, and it'll be smaller in relation to our charged particle, although that doesn't really matter what the charge is on our test charge, but it does have to be positive, okay? Because that'll give us a consistent direction no matter what the particle that we're testing is, right? So this is our charged particle. We want to know what the field intensity of this is. What is the strength of the force of the field that surrounds this charged particle? And so we bring in a test charge, a positive test charge, and we see what happens. Now we know that if I have a charged particle that's positive and a test charge that's positive, there's going to be a force of repulsion. It's going to be pushed that way. And so that is, in fact, the direction of the field that surrounds this charged particle. It will be away from it. Okay, so the electric field will be away. And that electric field surrounds this charged particle in all directions, right? It's just no matter where I put this test charge, it's going to be repelled by it. So it's going to be pushed away no matter where I put it. All right? And so that gives us a bit of a sense of direction. And if it was a negatively charged particle, that would be attracted to it. And so field lines, when we're drawing field lines around charged particles, those field lines will always go away from positively charged particles, and they will go towards negatively charged particles, right? Because, again, the test charge will always be positive, so it'll be repelled from positive ones, it'll be attracted to negatively charged particles. Okay? Now, how do we quantify? So that's the direction, but how do we quantify what the strength is? Well, it's quite simple. Right here, electric field intensity is this scripted letter E. Electric field intensity is measured in newtons per coulomb, and it's simply because the electric field intensity is the force that this charged particle will experience per coulomb, right? So it's force per coulomb, force per charge. All right, so what is the force per coulomb that it is? Now, our force, as we know from last week, is K Q1 Q2 over D squared, right? So if I make that substitution, then I get this formula, which is K Q1 Q2 over R squared over Q. Now, this Q is our test charge, right? This was our test charge. Okay, means this is our test charge. These two Q's, Q1 and Q2, these are our two particles. One's our charged particle, one's our test charge. What that means here is that one of these is the test charge, and they will cancel out, leaving us with KQ over R squared, where this Q is the charged particle, not the test charge. All right, so that gives us two formulas now for finding the electric field intensity, right here. Okay, so we have two formulas for electric field intensity. Again, depending on what information we're given, we'll determine which formula we're going to use. Right? If we were told to find the electric field intensity on a test charge with a certain amount of coulombs that experiences a force of a certain number of newtons, we would use our first formula. If we had the charged particle and a certain distance away from it, then we would use this formula down here. Okay, and we'll see that in some of the questions that we'll do today. All right, on the board next to me here, because as with all things in physics, there's a net force, and in this case, there's a net electric field. The net electric field is a sum of all the fields surrounding a charged particle. So if we have more than one charged particle and we bring a test charge into its region, there will be a net electric field that the test charge will experience. And so on our board next to me here, I've got some diagrams drawn, and we're going to take a look at that, and then we'll do a few sample problems. All right, so over here now I've got some diagrams drawn. Here I've got a positively charged particle and a negatively charged particle, and I've drawn what the field lines would look like surrounding it. So we have our field lines being drawn away from the positively charged particle and towards the negatively charged particle. And if I were to bring a test charge, if I were to put a test charge right into the middle here, that marker doesn't work. If I were to draw a test charge right in the middle here, we could see that it would be pushed toward and pulled toward the negatively charged particle. All right, and there would be a field intensity from both the positively charged particle and the negatively charged particle. If I were to put it up here, okay, now there's going to be a net electric field on it. Okay, so it's going to be being pushed away from the positively charged particle, but it's going to be attracted to the negatively charged particle in that direction, which will give us a net 1, which will be the sum of the two, and it will be in that direction between the two. And again, we would add those vectors by placing them tip to tail. All right, so this is the way the field lines look like when we have a positive and a negative, when we have oppositely charged. This is the way the field lines look when we have two of the same. Okay, I've drawn them as two positives, but they could be the exact same diagram if we have two negatively charged particles. Okay, and you see that there is this spot in the middle here where there is no electric field. All right, and that's just again like when you bring magnets together, when you try to push two magnets together, when you push two like poles together, you can't, right? They're very hard to get together because there's this negative space in the middle here where there is no electric field, or in the magnetic case, no magnetic force there. All right, so that's what this looks like. Now, how does this look like practically when we do some questions? Let's go back to the other board and we'll do a few questions. All right, here's our sample problem for this part of it. Our first example, it says that an electric field is measured using a positive test charge. And again, it won't always say positive because you need to know that all test charges will be positive. So a positive test charge of 3.0 times 10 to the negative 6 coulombs. The test charge experiences a force of 0.12 newtons to the east. And then the question is, what is the electric field strength? Now again, we have two formulas that we can use to find electric field strength that we just talked about. And in this case, we are given the test charge and we're given the force. So that tells us that we are going to be using the formula E equals F over Q. And we'll simply plug in our numbers, 0.12 newtons over our 3.0 times 10 to the negative 6 coulombs. And that will give us an answer equal to 4 times 10 to the 4 newtons per coulomb. Now, you will notice that electric field intensity, I've been drawing it with a vector sign over it because it is a vector, it does have a direction. And so here, if we had a charged particle, and again it's positive, it is experiencing the force in an easterly direction. All right, so that means that this electric field intensity is to the east. Okay, and so we want to continue making sure we write down directions for these. What this doesn't tell us is this doesn't tell us what kind of charged particle we're looking at, right? It just tells us what the field intensity is on this test charge. We could have a positive charge over here, because that would create an easterly one, or we could have a negatively charged particle here that would be attracting it to it. We don't know which the case is, and it doesn't matter for this particular question, but it could be either of these situations. The point is, this test charge is experiencing a force, 4 times 10 to the 4 newtons per coulomb in that direction. Okay, on our other board, we're going to do one more example, and then you'll be off doing an assignment. Here is example number 2 for us. This question is asking us, what is the electric field strength at a point 0.3 meters to the right of a small sphere of charge -4 times 10 to the negative 6. So what this question is saying is we have a negatively charged particle here. We have a point 0.3 meters to the right, so somewhere over here, 0.3 meters. We have our test charge. And again, remembering that test charges are always positive. And so we want to know the electric field strength at that point. So now, because we have the charge on the charged particle and we have the distance, we're going to use the other formula for electric field, which is KQ over R squared. And we'll put in our numbers here. Remember that K is 9 times 10 to the 9 newtons meters squared per coulomb squared. Our charge is 4 times 10 to the negative 6 coulombs, and our distance is 0.3 meters squared. You will notice that I did not put a sign with our 4 here. And that's because, again, the sign is just an indicator that this is a negatively charged particle, and it doesn't go into the math here necessarily. If you put it into the math, that's okay, you'll get a negative answer, and you just have to know what that negative answer means. I'm going to leave it as positive, and then we're just going to use our diagram, because the positive and negatives just gives us direction. And so I'm going to use our diagram to get direction rather than the positives and negatives in the math part of it here. All right, if we punch this in to our calculators, you should be able to get the answer negative 4.0 times 10 to the 5. And this would again be newtons per coulomb. And now we want to figure out which is the direction of this field. Now again, we're looking at the field intensity from the perspective of this positive particle, right? And so the field here, it's not negative, sorry, it shouldn't be negative. I was going to leave out the negative signs. Right, if you had the negative here, you'd get a negative here. I'm not going to put the negatives in, so we're going to get an answer here, and we're going to look at our diagram for the direction. All right, so again, the field intensity is as experienced by the test charge. And so this test charge is going to be drawn towards the negatively charged particle. Remember, field lines go towards negatively charged particles. And so this charged particle, the field strength, would be 4 times 10 to the 5 newtons per coulomb left. Okay, and so I don't like putting the directions in here because we would have the same situation if the positively charged particle was on this side, but then if we put negatives in, then the negative would be to the right. And I just don't like that because we've always kind of said that we take signs and direction. Positives means to the right, negative means to the left. If you put the negative in here and this charged particle is on the other side of it, you got to be careful with signs. I'd rather do it without signs in the equations and use diagrams to come up with the direction. So that's what I would like you to do as well. Okay, hopefully these two examples will help. We are going to do a few questions now out of your textbook. There are 10 of them that I would like you to do. And so you can check on Connect for that assignment. I'll say it here as well. It is page 565 out of your textbook. There are 5 questions on that page, 565, 1 to 5. And then if you flip the page to 566, there are 5 other questions there, 6 to 10. And so I'd like you to work on that. I will tell you too that tomorrow there's not going to be any new lesson. There's just going to be a few more questions on this. So tomorrow in our video we'll be going over some of these questions as well as assigning a few more, so there won't be a new lesson tomorrow. And so if you don't get all 10 questions done today, that's okay. You can continue working on them tomorrow along with some other stuff. And again, I'll remind you that we do have a long weekend coming up. 4-day weekend, because Friday is Good Friday, of course, and then the following Monday is an administration day as well, where there won't be school that day. So you've got some time to get some stuff done over the next little while, but don't put it off too long. All right, have a great day. We'll see you tomorrow.